This video discusses a caveat which we must consider when we're integrating things in polar or spherical polar coordinates, and that caveat is the volume elements of those integrals. So let's say we have an integral over f of x from minus infinity to infinity. That's over the entire range of the function. We would call this an all-space integral, whole space integral, something like that. So we might specify this in shorthand by doing something like the integral with an r down here, an integral with an r down there, indicating, that's the word I was looking for, indicating that it's over all real numbers. So that indicates we're over all real numbers. And remember, this dx here means some infinitesimal, some very, very tiny change in x. Okay, so in 2 dimensions, we'd have the integral from minus infinity to infinity of dx, integral from minus infinity to infinity of dy, times f of x and y. So that would be the all-space integral in 2 dimensions. So since that is in 2 dimensions, we could write that as the integral over r squared, indicating that it is from negative infinity to infinity in x and y. So integral over all real numbers in x and y of f of x, y. Similarly, we could go to 3 dimensions and repeat this process, x, y, and z, f of x, y, z, integral over r cubed, and you could say dx, dy, dz, you could say d tau, you could say dr cubed, dr, indicating an r vector, times f of x, y, z, but just making the point that there are many different ways we could say these volume elements for these all-space integrals here, for what the bounds of integration are in each of the variables. Okay, but let's say we have a 2-dimensional function and we integrate that in x and y, but we instead don't want to do it in x and y. Maybe it's an easier function to write in r and theta. So if we want to go from an integral over all space in x and y to an integral in r and theta, or really any kind of bounds you like, what do we need to do? Well, number one, we need to change the bounds of integration, because x and y go from minus infinity to infinity, and r and theta go from 0 to infinity and from 0 to 2 pi. So that's one thing, is to change the bounds of integration to the bounds of those variables. But another thing to change is that the volume element is now different. dx dy is equal to r d theta dr. It's not equal to d theta dr. There's an extra r in there, which we'll discuss shortly. Similarly, in spherical polar coordinates in 3 dimensions, the all-space integral over 3 Cartesian dimensions, x, y, and z, of f of x, y, z, maybe it's easier to express the function as a function of r, theta, and phi, the spherical polar coordinates. And in that case, you need to integrate from 0 to 2 pi in phi, 0 to pi in theta, 0 to infinity in r, as are their dimensions. But there's this extra factor again. There's a factor of r squared sine theta. So let's discuss where this comes from. Okay, so in 2 dimensions, we can imagine we're integrating over the entire xy plane to find the volume under the entire surface. So we have x and y, and then dx and dy are little infinitesimal changes. So dx dy is a tiny little square in this plane. So this is our tiny little volume element, the amount that we're integrating here, dx dy. And no matter what values of x and y we choose, these are the same amount. They're always tiny little changes in x and y. Now let's go to polar in terms of r and theta. Now let's imagine we have some tiny change in r, dr. That's a distance again, so it's fine. So that works the same. But now let's imagine this tiny change in theta here. On our surface here, this theta isn't a distance, theta is an angle. So this little arc on our circle here is not d theta, it's r d theta, because it scales with the distance that we go out. It scales with the circumference of our circle. So this, in fact, this little volume element here is dr times r d theta. So that's why when we go from dx dy, our volume element goes to r d theta dr. So we get our volume elements going from dx dy to giving us our extra factor of r there that we need to worry about. Then when we extend this into 3 dimensions, it's harder to write in 3 dimensions because it's 3-dimensional, obviously. I have a 2-dimensional medium to talk to you right now. So the values of dx, dy, dz in the little cube that we're integrating, because remember, 2 dimensions, it's a little square, 3 dimensions, it's going to be a little cube that we're integrating over. So in spherical polar coordinates, that's going to be the length of each of these three is going to be dr, and then theta works like phi works like theta in polar, so it's r d phi for that length. But then the most complicated one is in terms of theta, which becomes r sine theta d theta, which you can convince yourself of if you work through it enough. So these together give us dx dy dz is equal to r squared sine theta dr d theta d phi. So that all together gives us the total volume element we need when going from an integral in xyz to an integral in r theta and phi. So take care that when you're doing an integral in polar or spherical polar coordinates that you remember the correct volume elements and bounds of integration, because it is extremely, extremely likely that you will not only have one of these types of integrals on a homework set, but you will have one on a test, and you will probably have one on the final exam. So take care to note these volume elements in polar, but especially spherical polar coordinates.